Hello everyone, welcome to lesson 12.2. We're going to talk about vectors. Hopefully this is a familiar subject, but if you do not recall anything about vectors, we are going to start from scratch here. So the first thing you need to know is what is a vector. A vector is a special kind of number. It's different than numbers you studied before that because other numbers, they're called scalar numbers, just give you scale, a number, 5. It could be 5 trees. It could be $5. It tells you how many. That's all it tells you. And so we need numbers that describe things that move. So now we have a way to talk about motion and vectors, which have two ideas built into them. One is magnitude, which is kind of your scalar idea, and then the other is direction, because it represents the movement of a physical object frequently, seen or unseen. We need to be able to have those two features, speed and direction, built into our numbers. So let's take a look at a vector here. We have the initial point and the terminal point, and the arrow points toward the terminal point and is different than a ray in geometry. An arrow in geometry on the end of a line segment makes it a ray that extends forever and has an infinite length. Unlike a vector has a specific length. The arrow is merely an indicator of the direction of the movement. So we could put the arrow on this end and we would be representing travel toward A from B. So the arrow is necessary, a part of the graph. If you have to draw a vector, you must include an arrow. Naming of a vector, there's a couple of ways to do it. You can use the endpoints and put a bar over it. This is very much like we would do in handwriting. In your textbook, you will see without a bar, but these letters will be in bold. And handwriting, we don't really expect you to bold your handwriting. That would be ridiculous. So in a book, you'll see it bolded, but in handwriting, you'll see a bar over it. And when they do describe it with 2 points, often in the book, they'll adopt the handwriting practice. So I want you to think of a vector as a directed line segment. Segment because it has a beginning and an end, and directed because it has more than just length to it. It has direction. All right, so moving on, we have diagrams that show vectors. These look like tangent pathways coming off of this curved pathway. So if the blue curve, which we will discuss how to define curves using vectors at a later time. But if the blue curve is a direction of motion for an object, then V for vector here could also be representative of velocity. And velocity is how fast something is moving and what direction it's moving in. So a perfect example of a vector quantity. And some people often ask me, well, can't it just represent the velocity? Well, velocity is a two-component idea. It's speed and direction. So what people are thinking of when it's not the vector quantity, they're thinking of speed. So the absolute value of velocity is speed, but velocity always includes a direction. Speed is just a scalar number. So that illustrates a need for this kind of quantity that goes beyond just a scalar number. All right. So check my notes, make sure I'm including all that I want to say. So here's our definition of equal vectors. Okay, so right here we have 4 vectors. They are all the same length and they're all parallel, and therefore they are equal to each other. They would write that AB vector is equal to CD vector equal to OP equal to EF. And so this statement includes the idea that they're all the same length and that they would all make the same angle with the x-axis, were they all positioned with their initial point at the origin. Okay. So in essence, they're all the same vector, and here's where we learn that a vector is not married to its position in the plane. It is absolutely not required to be represented sitting at the origin, but it often is. A vector whose initial point is at the origin is called a position vector. So when you see the word position vector, they are implying that the initial point of the vector is sitting at the origin. Okay? So moving forward, here we go. With the formula to calculate the magnitude or length of a vector, you can use these two words interchangeably, as I will. So our vector that we're interested in is PQ. So it starts at P and ends at Q. Now, they moved it down so that P is at the origin and now it's called a position vector, like I said before. And our components of this vector, see the terminal point is v1, v2, v3 for a coordinate triple, and the representation of the vector with the bent brackets here is v1, v2, v3, indicating that that's how you get from the initial point to the terminal point. You would go v1 units in the x direction, and they actually drew that down here, but I would put it here. v2 units in the y direction, and v3 units in the z direction to get to the terminal point. So the components here tell you how to get from the initial point to the terminal point, and when it's written like this, you really don't know where the vector should be drawn, so you get to choose where to draw it. Now, the formula for magnitude is highly predictable here. Looks a whole lot like the distance formula in 2 dimensions. So we add in the third dimension over here. That is going to give you the length of v3 here, right there, is the difference between the z coordinates of the endpoints of the vector. So this should be a simple augmentation of your 2-dimensional distance formula. Okay. So they did use these symbols in the previous picture, so you might have an inkling here. A vector in 2 dimensions, typically in the xy plane, but doesn't have to be in the xy plane, represented with 2 components. I will say if I write a vector with 2 components, you can count on it being in the xy plane, okay, as a practice. When I want to include any other direction, I will include the third component, and these will always represent x, y, and z in that order. If I wanted a vector in the yz plane, I would represent it this way rather than just use 2 components, because I told you I'm going to default to 2 components being x and y only. Okay, so it's not a bad idea to represent in 3 if you are going outside of the xy plane, even if you're only using 2 components. Okay, so the head minus tail rule, I'm not sure your book ever called it this, but this is the easy way for me to remember this. HMT, head minus tail, is a method for finding the 3 components of a vector given the endpoints. So if the initial point of the vector is x1, y1, z1, and the terminal point is x2, y2, z2, then and the terminal point is also the head of the arrow. So that would be head minus tail. So this is the tail of the arrow. So think about, especially like a traditional arrow, like if you went bow hunting. It's got little feathers on the end here. The head is the terminal point of a vector, and the tail is the initial point of a vector. So if we do head minus tail, that's x2 minus x1 to give us the component in the x direction, y2 minus y1, and z2 minus z1, giving us the y direction and the z direction. Nice little way to remember that rule. Okay, so, oh, by the way, I did leave out a minor point here. When we represent the magnitude of a vector, we put little bars around the name of the vector. I will mention that occasionally, maybe in physics class or some other textbook, you might see double bars. And that's also a different symbol for magnitude. Some books adopt this one. I prefer the one in our book because it's just less to write. Remember the vector representation. If we give it a single letter name, it's lowercase. And in handwriting, we would put the little bar above it. In print, we would just make it bold, but there's no such thing as bold handwriting. So if you are writing the name of a vector, make sure you put the little bar over it. And then you can do either a single pair of bars or 2 pairs of bars around it to indicate magnitude. Alrighty. So let's just do a sample problem here. If you want to pause the video and try this problem, when you come back, I will explain it to you. Go ahead and hit pause now if you're going to. Okay, so here we go. Find the component form and the length of the vector with initial point P and terminal point Q. So component form is going to be the head minus tail rule. So here's the head and here's the tail. And so we're going to say that vector PQ, put a bar over it, is going to be, we're going to use bent brackets, -5 minus -3, 2 minus 4, and 2 minus 1. So negative 5 minus negative 3, 2 minus 4, and 2 minus 1. And that's going to give us negative 2, negative 2, 1. So there's the component form of vector PQ. And then the length of the vector, now that we have the component form, the length of PQ is going to be negative 2 squared plus negative 2 squared plus 1 squared, which is square root of 4 plus 1, or the square root of 9, which is 3. So those are simple calculations. It's always nice to start off easy. So now we're going to look at an application, and example 2 is nicely given us a picture. So we've got a small cart here in green. It's being pulled along a smooth horizontal floor with a 20-pound force F, making a 45-degree angle to the floor. So this is a rope or something pulling on that cart. They want to know what is the effective force moving the cart forward. They want to know this force right here. Okay, so this is a question you can answer with basic trigonometry if you recognize this. If you're going to put a horizontal line here, we simply need the length of the opposite side of this little triangle. And so notice they didn't give us, well, they gave us a 20-pound force for F. So that would be the magnitude of F. And we want to know, and let's see, we can call this A right here. So A is going to be this length. B is, actually they're both going to be A, aren't they? Because this is a 45, 45, 90. So we can just call both the horizontal and vertical components A. So A is going to be the length of F times, and since it's vertical, we're going to do, oh no, they want the horizontal, excuse me. We're going to do the cosine of our angle down here, 45 degrees. So we've got the length of F is 20 times the cosine of 45 degrees. So we're going to have 20 times 1 over root 2, so 20 over root 2. And if you're really picky and you want to write this as 10 root 2, that's okay. This is okay too. I'm going to say you are officially relieved of your duty of getting rid of radicals on the bottom. Not that it's so hard to do, it's just that when you start having algebraic expressions under your radicals, then it gets to be more work than you care to put on the page, and messier to read. So less simple, not more simple, but I would accept either answer here. If you were not asked to round, then please leave an exact number. So this is going to be pounds. Make sure you always put units. And so we have an effective force of 10 square roots of 2, which is what, 14.1 pounds if you had to round. So you can represent these pictures with vectors just as easily as you can represent with basic trigonometry. So the mathematics is not hard. It's just the new thinking with new symbols and such. Okay, so here's some basic rules. We learned about a new kind of number, so we have to learn about its rules. And so they're defining the u vector to have the components u1, u2, u3, and then the v vector similarly. This is a very common convention that they will name the vector and then use variables with the same letter in them for the components. So these are vectors u and v with k a scalar number, a scalar quantity, just a plain old number. So the way that you add two vectors is happily easy. You're just going to add the first components together, add the second components, add the third components. Now, this is not a geometry definition, this is an algebra definition. So scalar multiplication, multiplying a vector times a scalar number. So k times the vector u, we're going to just distribute the k to the various components. This multiplies the length of the vector times k. I will say they didn't specify that u was a unit vector. And we'll talk about unit vectors, a vector that's 1 unit long, but sometimes in this book when they use u, they mean a vector that's just 1 unit long. So when we get to that, we'll talk about a symbol that'll help you know that. Okay, so now we need to know the geometric representation of what it is to add two vectors. So if we look at u and v, and we start at the origin, so make u a position vector, and then if we want to add v to it, we put the initial point of v on the terminal point of u, and then draw v at the appropriate angle. And to get the vector of u plus v, we're going to have to draw from the initial point of u to the terminal point of v. So this pink vector represents the vector u plus v. So this is a pretty easy thing to remember about what it means geometrically for two vectors to be added. Here is another way to represent it. If you draw both u and v from the origin as position vectors, and then see how they've made this into a parallelogram? This side of the parallelogram here is equivalent in length and direction to v. So this is also v, basically. And over here, parallel to u, this is u. We have a cat coming this way that wants my attention. Okay, you'll have to pardon her if she steps in the middle of the video. So we basically duplicate u and v, and it makes a parallelogram. And then this same pink vector, u plus v, is the same vector we had over here, since they're both u and v are the same quantities as they were here. But that's the cat's doing. This parallelogram is a much more common way of representing the addition of vectors. It's the diagonal from the origin to the opposite corner of a parallelogram. So the reason why this is a good definition is because it's related to the definition of subtraction as well. Okay, so yeah, this is called the parallelogram law of vector addition, maybe because they like big words. Okay, so scalar multiplication, if we've got u here, and it's going in the direction the arrow indicates, 2u would be twice as long and going in the same direction. 1.5u would be 1.5 times as long, and negative 2u would be twice as long but going in the opposite direction. So that's a pretty simple concept. We just always want to make sure we understand the geometric representation of an operation if it exists, okay, which implies that it won't always exist. So now I told you we'd see subtraction. So in graphic form, and keep in mind this could be the origin or not. If we are saying u minus v, we're going to draw u and v originating from the same point, with terminal points heading away from this point, and then going from the tip of the second one back to the head, I should say, the head of the second one back to the head of the first one, those terminal points. This pink vector represents the quantity, the vector quantity u minus v. So this is the physical representation of subtraction. And let me show you how it relates to addition. If I drew that parallelogram in, you could see that this diagonal is vector addition and this diagonal is vector subtraction. And you have to make pains to put the arrow on the proper end. You're basically going to the end of the second vector, the terminal point, and drawing your vector in the direction of the first vector, so that the tip of your subtraction vector meets the arrow of your first vector in the expression. Okay, take a little while for you to remember that. Here's yet another representation of subtraction. So you've got to realize that u minus v is the same thing as u plus negative v. So we've got u here, and instead of drawing v from the origin of from the same initial point as u, they're just going to call it negative v and add it by putting the initial point of v on the terminal point of u and going in the opposite direction of the original v. So u plus negative v gives you this diagonal, and that would be the same representation, the same length, the same direction as u minus v up here. So there's two different ways to represent subtraction. Okay, so fortunately the arithmetic is super simple. If you want to pause here and come back and see if you're right, that's a good idea. All right, so for A, we've got 2 times negative 1, 3, 1, plus 3 times V is 4, 7, 0. So that gives us negative 2, 6, 2, just distributed, and 12, 21, 0. Now we have to add. Negative 2 plus 12 is 10. 6 plus 21 is 27. And 2 plus 0 is 2. So there's vector addition. Vector subtraction, u minus v, negative 1, 3, 1, minus 4, 7, 0. Just straight up subtraction. Negative 1 minus 4 is negative 5. 3 minus 7 is negative 4. and 1 minus 0 is 1. So what could be easier than the arithmetic part? You might be asked to draw a picture of this. That would be a skill that I would want you to have. Okay, the length of 1/2 u is going to be, okay, first of all, the length of 1/2 of -1, 3, 1. Okay, so I'm being very formal here, by the way. Distributing -1/2, 3/2, 1/2, and then take the length. So the length is going to be -1/2 squared plus 3/2 squared plus 1/2 squared. All right, so we've got 1/4 plus 9/4 plus 1/4 is the square root of 11/4. And I would not want you to leave a fraction under a radical, so please say the square root of 11 over 2. Okay, so there's some good samples of arithmetic with your vectors. Okay, these are all kinds of properties. I'm wanting to know if you could identify, based on what you remember these words mean, to identify which property is which. Okay, so let's see, did I make this so that, oh, it doesn't move. Okay, so we're going to have to just list which one is which up here. Take this time to pause, see if you can put the numbers of each of these beside these. Notice there's 9 of these and only 8 of those, so we'll see what you make of that. Okay, so coming back, we've got the order is reversed, so that's the commutative, so property of addition. And adding a 0 vector. Notice this is bold, so this is actually the 0 vector, which is a vector with 0 length. It is considered perpendicular to every vector, and we'll talk about that further when we talk about what perpendicular is for vectors. We're starting with u, adding 0, and ending with u. This is an identity property, and it's addition, so the identity property of addition is here. Oh, these are numbered back and forth. Okay. So here we're just grouping together different vectors, so that's the associative property. For adding the opposite, that's inverse, since we're doing the inverse of addition is adding the opposite, so inverse property of addition. All right, 0, scalar 0 times a vector is a 0 vector. That's obviously the one that's dealing with 0 multiplication here, so that's 5. And then 6, 1 times u equals 1. This is the identity property of, instead of addition this time, it's multiplication. And then, again with the grouping, here we're multiplying a scalar b times the vector u first, and then multiplying by the scalar a. Here we're multiplying the two scalars together and then multiplying by the vector, so that's just associating together multiplication in different groups. All right, so we've got a times the quantity u plus v is au plus av, so that's the distributive property. And here's just another version of the distributive property, that's why it's only listed once. See, used twice. So that would be 8 and 9. Okay, hopefully you're familiar with the names of properties, and if you're not, then this is a good little practice to go back through. Okay, so unit vectors. I said we would talk about unit vectors, and this is a different way to represent components in a vector. Notice that I and j and k are bold, all right, and down here we have vector I, vector j, and vector k, and vector I is a unit vector. In fact, these are called the standard unit vectors. The meaning of this whole phrase together is that these 3 vectors make up a coordinate graphing space, okay? So vector I would be considered the vector 1, 0, 0. And j would be 0, 1, 0. And k would be, well, that was terrible. You can laugh at my bad handwriting, by the way. 0, 0, 1. So these are the standard unit vectors that establish 3 space as we are drawing it in this course. And so multiplying a scalar number times each of our standard unit vectors would tell you the 3 components. So another way to represent this vector in component form would be x2, y2, z2, but this is in standard unit vector form. And I don't know that that's an official vocab word. I do know that this is called component form with the bent brackets. Never been given an official name for this, so I just know that it uses the standard unit vectors. A lot of times I'll just call it IJK form. All right. So they're representing the head minus tail rule here in IJK form for the vector P1, P2.